Hi, welcome again to another session where we'll be solving one kind of typical examples or problems that you're going to find in this topic, which is trying to find the principal stresses from a stress tensor. Basically, this is what we have done in kind of the whole derivation we did in the previous lessons, where we started from a point instead of a body, and then we went through certain steps, such as using kind of beneficially for us the equilibrium conditions such as rotation equilibrium and translation equilibrium. Then we went to determine what was the situation when a stress was on an incline or applied on an inclined plane. And then after that, well, we needed to, we used for that purpose direction cosines. And after that, we came up finding out a plane or that is oriented in a certain way that there are no shear stresses, but there are only normal stresses. And we came up with this idea of principal stresses. And later, or after that, we came up with the idea of the principal directions. Maybe it's not the proper way to say that we came up with the idea, because this is already discovered, invented, but we showed how we got from the point in the body to demonstrate or to present by simple derivations that there exists this plane where there are only normal stresses. In this case, we're given a stress tensor, and we need to find the principal stresses from this stress tensor. And this is a pretty basic and simple example. If we wanted to find these principal stresses, the first thing we have to do is to apply our third-degree polynomial that we found for principal stresses. Let's remember that that equation, I'm going to write it in green, is something like this. Is sigma 3 minus the first invariant times sigma 2 plus the second invariant times sigma minus the third invariant, and that's equal to 0. This is the equation we have to solve. This is going to give us 3 real roots, and those real roots are going to be the principal stresses. And let's remember that we have to sort these principal stresses from the largest to the smallest, being sigma 1 the largest and being sigma 3 the smallest. And that's the way we're going to represent our principal stresses. It's pretty straightforward problem in the sense that we're given the stress tensor here, and we just need to calculate each of the invariants from the tensor and then solve the roots of this polynomial equation. We saw that, or I presented to you 2 different ways of calculating this invariance. So you could choose any way. You could choose the, let's say, the normal already, say, open up representation of an invariant, or you could use the determinant representation or matrix representation of an invariant. In this case, I'm going to use the open case. I'm going to write all the terms that corresponds to each one of the invariants. Let's see. We know that the first invariant is something like this. I1 equals to, it's basically going to be the sum of the diagonal terms in the matrix. It's going to be sigma XX plus sigma YY plus sigma ZZ. We're talking about these 3 terms here. This is also what is called the trace of the matrix, sorry. Following here, this is going to be equal to 6 plus 5 plus 4. And this is going to give me, I already have calculated this, so just in order to save time during the resolution of the problem, this is going to give me 15 megapascals. Well, perfect. My second invariant is going to be a little bit longer. Let's remember or check out the previous video where I showed how to derivate or how we came up with this third-degree polynomial equation. In this case, it's going to be sigma xx times sigma yy plus sigma yy times sigma zz plus sigma zz times sigma xx. It follows like minus tau xy square minus tau yz square minus tau xz square. If I substitute all the values here in this equation and put a line here to separate things, this is going to give me, I'm going to delete this one here. It's going to be sigma xx times sigma yy. Again, if you cannot remember this, please try to memorize how a stress tensor looks like. Remember that in our case, a stress tensor is something like this: sigma xx, tau yx, tau zx, tau xy, tau xz, sigma yy, sigma zz, tau zy, and tau yz. So you can have this guide here. It's going to be then 6 times 5 plus 5 times 4 plus 4 times 6 minus tau xy. We're talking about this one here to be 1 square minus tau yz, and tau yz is going to be this one here. And because we can use reciprocity of shear stresses, that's why these two terms are equal, these two terms are equal, and these two terms are equal. So if I say tau yz is equivalent to saying tau zy, then yz is 3 square minus the remaining one, the square. And as I mentioned, I already calculated this, and this is going to be equal to 60 megapascals. Now, the third invariant is a little bit longer than the second one, and it's going to be, the formula is going to be sigma xx times sigma yy times sigma zz minus sigma xx tau yz square minus sigma yy tau xz square minus sigma zz tau xy square plus 2 tau xy tau yz tau zx. Good. Substituting the values here, I will have 6 times 5 times 4 minus 6 times yz 3 square minus sigma yy 5 times xz, it's going to be 2 square minus 4 times xy, it is going to be 1 square plus 2 that multiplies 1, 3, and 2, and that's going to be equal to 54 megapascals. Now, having calculated the invariance, I can formulate my complete equation for principal stresses, and that is sigma to the power of 3 minus 15 sigma square plus 60 sigma, then it comes minus 54, and that should be equal to 0. By plugging in this equation into a calculator that is a kind of with possibilities to solve polynomial or roots, polynomial roots, then you're going to find that the solutions to this equation are in the order kind of sigma 1 bigger than sigma 2 bigger than sigma 3. It's going to be equal to 9 megapascals larger than 4.73 megapascals larger than 1.25 megapascals. Write it a little bit better. And this is kind of the equivalent to this. The sense that this corresponds to sigma 1, sigma 2, and sigma 3. And there you go. You have found a solution for the equation of principal stresses. Look at this. So if I look at the stress tensor, I can notice that the largest stress in this tensor, or let's put it in this way, the largest normal stress is going to be 6 megapascals, this one here. This is the largest one. So you would be kind of thinking that, okay, I can use the principal stress or the stress tensor, and then I can extract from the stress tensor what's the largest stress, and then compare it to, for example, the yield stress or any other material stress used as a selection criteria. However, when you find this plane where these principal stresses are, and you calculate these principal stresses, you find out that actually 6 is not the largest stress present in the body, but it's 9. By the way, this could be positive or negative depending on how the calculation goes, but it's not 6, but it's 9. So this is kind of one thing that is going to give us more tools, more safety at the moment of selecting our material when we are designing our parts. It's a pretty straightforward procedure. It's simple. It's nothing compared to what we have done to derivate this polynomial equation to find out the principal stresses. That's all until now. I hope that it was clear enough that you can follow it and do it by yourself. And one exercise, extra exercise that you could do is to calculate the principal directions. I said that there is a formula for that, so we have already derived the formula to calculate the principal directions, and it is, again, it's a pretty straightforward procedure. Direction, no way, but directions, yes. So search for this. Thanks for watching, and see you soon in the next video. Take care.